Okay, so next we're going to shift gears and we're going to get into liquefaction. And one of the things that I didn't realize about SmartDry was their application to dredging, which for the DoD and Navy people here on this call, that would have a huge application. It was not in Fernando's presentation, but he will talk about it briefly, and he's going to get me some information to put up in the document repository to discuss that. But the idea here is to be able to strip out valuable metals and contaminants from dirt, sand, soil, and to clean up the soil, to be able to monetize the waste that different processes are producing. One of the things that really hit home with me, and Ryan Polterman, I'm going to want you to listen to this, is has to do with separating out uranium. And is that correct, Fernando? So
yes.
Taking out uranium deposits from within the soil. We had discussed before about being able to clean up areas that may have been contaminated with like metals and things where they had been a dump before, and being able to clean up the soil. So there's a lot of applications here, and that's one of the beauties of this technology. So at this point, I am going to turn it over to Fernando from SmartDry and let him explain to you what it is that he does and where he wants to take it. And just to let you know, Fernando, Ryan is with Department of Energy.
Okay, thanks a lot, Eugene. Let me start sharing my screen. And as Eugene just said, we are SmartDry. We are a hard tech company that we invented two new processes. One is for dewatering in mining, and the other one is a broad application for mineral separation that can be applied to different problems and pains in several sectors. One of them is inverted leaching, and it was what Eugene was talking about. We are in the phase 0 of the DOE program, especially working with the problem of extracting uranium from ores and from waste, tailings, and even so also to test if we can remove contaminated soil, remove the radioactive material from contaminated soil. Well, the leftovers of the Manhattan Project in the United States. So in terms of leaching market size, it's huge, right? I mean, all these metals here are leachable, and it is a growing concern that mining companies are moving from smelters to leaching process due to the problems of greenhouse gases and things like that. So it is presently a trend to do using leaching process. In terms of the value, right? Metals is behind only of crude oil, right? I mean, gold, copper, aluminum, nickel, zinc are all leachable metals and can be recovered using this technology. So in leaching, when you're talking about leaching, you have to understand there is two areas. One is the chemical area, which for almost every single material or ore, it's quite well known. There is a recipe there for what is the process, what are the chemicals involved and things like that. And then there is what I call the mechanical side of leaching. Then in this term, there is the heap leaching, tank leaching, and in situ leaching. Well, heap leaching is basically this. You make a pile or a heap and you drip the lixiviant and it percolates down, you recirculate it, and then you end up having a solution, a pregnant solution with a leachable material. The problem with that is that there are a lot of problems with the formation of preferential channels and things like that that end up being translated in a low efficiency. You can recover from between 50 to 80% of the leachable metal in your pile. So it's not very efficient, but it's very cheap. That's why. So if you have a very low concentration of leachable metals, this was your choice. When you're talking about tank leaching, it's a much more complex, much more expensive process. So you need a very rich ore or material to do so, to make it viable. And in this process, the material is floating in a contraflow, but it's floating. So we say this has low energy impacts between the grains and the lixiviants and so on. It's a very high efficient process. It can go up to 95% recovery rate, but very expensive. So for high grade ores only, which are diminishing because we have mined the most high grade ores already. So if you compare inverted leaching with bio and tank leaching, in situ leaching, it's a very specific problem. In the United States, is 50% of the uranium is in situ leaching. But again, it's a very passive process. So if you compare inverted leaching, bio and tank leaching, the extraction time, the amount of lixiviant used in inverted leaching is much lower, which reduces the cost upstream. And during the process of inverted leaching, we recover also the non-soluble, the insoluble metals in the process, which in bio and tank leaching is also not recovered. This is important because the insoluble metals left behind can generate what is called acid mine drainage, which has an environmental impact and a problem. So we recover leachable and not leachable metals in the same operation. So here is just a video showing you how this is done. What happened is, this is manganese waste, right? So water is being injected here. If you replace the water with the lixiviant solution, you clearly understand what's going on. So you can see the material, the water is rising through the material, so the grains are rubbing against each other, and this will help the extraction process. Once you reach a point there is a liquid layer form on the top, you can start recirculating this liquid as many times as you need it to recover the full extraction of the leachable metals present, right? So this is something quite new in terms of leaching process. And it can be done in one step or in two steps way, depending on the characteristics of material we're dealing with. One step, you put the material aside and start circulating the lixiviant and extracting. The two steps process, first you do with the water to create a concentrated metal layer, and this is what you put in the equipment, and then you circulate the lixiviant solution. The idea here is that you're gonna reduce the volume of lixiviant and in being more efficient. So the other solution is dewatering. Dewatering is a major problem right now in the mining sector. 75% of the mining around the world is done in water stress places where water is a problem. And dewatering is a huge problem in mining because the volumes we're normally talking about. We're talking about millions of tons in a single mine, and this creates a real problem. In the past, there was not a problem because the mining companies put them in the tailing dams. After the disasters in Brazil, there is a global awareness, and the laws and rules have changed, and now it's not more acceptable to have very wet tailing dams. So basically what is happening is that mining companies are looking for a solution. Presently, the mechanical solutions available are press filters, disc filters, and centrifuge. They cost a lot of money, they use a lot of energy, because they have to transform the electricity in a form of a force, either hydraulic or a suctioning vacuum or centrifuge force, to extract the water. In liquefaction, the water is extracted by the fact that when you apply vibrations, the grains become more well fitted, closer together. And there is a difference in density between the liquid and the solid. So once the grains fit well together, the water has no other place to go but up and forms a liquid layer on the top. You remove that liquid layer and you get a material that is called dry stackable. So again, let me show you this really happening here. You apply vibrations for 1 minute. Oops. This material is 50% solid, 50% water. You apply vibrations for a minute and you end up having a dry stackable material, right? And this is the beauty of it. Once this material has passed a liquefaction effect, it will not undergo liquefaction again because there is no enough water to do so. So you can put this material on the ground and compact it, which is what the mining companies are looking for, a solution to compact the materials. So in terms of funding, we are in the phase 0 of the DOE program. We already submitted our letter of intent, and now we are finishing the detailed project. We're going to upload and SAMs grants and other things. In Brazil, we got a grant from the Brazilian Ministry of Science, Technology, and Innovation, and also from our small business agency, it's called SBIR here. So this technology, this mineral technology, like Eugene said, it has a very broad application. Swapi port and the port of Rotterdam. Why? Because we want to change the way dredging is done. It's a quite bold statement, but it's actually true. Dredging, since it's been invented, it is a process where you take the dirt from one place and dump it in another. This is not sustainable, it's pollutant and not logical. What we want to do is bring mineral separation to the process. And in doing so, we're going to separate the organic matter, the sand, and the metals. The organic matter we're going to use as fertilizer in agriculture. The sand will go to construction and other things, and the metals recirculated as in economy, circular economy solution. The beauty of it is that the equipment can be done in any size, so we can do it. And we're going to propose to the ports that instead of having a dredging just when you are at a crisis, that meaning your port is being facing a problem with deposition of materials, it's better to do dredging all year long, let's say. And this will reduce the volume in terms of dredging and allow us to separate this and sell this. In terms of how profitable this can be, in terms of Brazilian prices, which is very different from the United States or Europe, selling the dredging parts can generate as much as the cost of dredging itself, as amazing as it may sound. We made some calculations in Brazil already, and it's incredible because there is a crisis in the sand. I know it may sound incredible, but sand is the most mined thing that we use around the world. We mine 50 billion tons of sand every year, and we are running out of it. Because there's a lot of sand in the sea, but it's salty. And in our process, we're going to use fresh water from low tide to desalinate it as we do mineral separation. So this is SmartDry, and I'm ready to get your questions.
Was that your dog?
My neighbor's dog.
Oh, okay.
Sorry, if it was my dog, I was already screaming at it.
All right, Ryan, you got something?
Yeah, I was wondering if there was an existing requirement that the material to be separated is the sole solid ingredient.
Not really. The material will be separated based on two main things: its density and its grain size. So
okay,
it's pretty much doable to any kind of material, apart from things like, for instance, calcium carbonate. Okay, calcium carbonate, it's sometimes a waste from mining, and calcium carbonate has a high affinity with water, very high affinity with the water, and this does not go well with liquefaction. Right? I recently tested manganese, like you you saw in the video, and manganese came up with a nice surprise. Manganese is also a dipole molecule, and this interacts with the water in a way that the very, very small grains of manganese are dragged along with the water. When we saw this, we were talking to a Canadian mining company, and they said, wow, this is something that we were not expecting. I said, yeah, but this is an opportunity. They say, how? I said, well, if we can separate the very, very small, the ultra for grains of manganese, we can use that for the electric battery sector. But they are looking for these kind of things for those batteries that use manganese in the composition. And the guys went, oh, can be done. I say, I don't see no reason why. Once you have separated the very fine, ultra fine grains, all you have to do is calcinate it. Of course, there is dirt with it, but the difference in density between manganese and the dirt is so high that you can use a density column to separate the manganese and leave up the dirt. The Canadian company is thinking about it. Mining companies are slow, big companies. Anyway,
I follow.
Yeah, go ahead.
The other question is, what sort of scale are you currently operating at?
My lab equipment can handle up to 15 kilograms per test, per batch. I'm looking for funding here in Brazil to get grants to build a pilot plant that will handle between 10 and 20 tons per cycle. In Brazil, this is being a challenge because the mining companies want to have the solution ready. Right now, I'm talking to a mining company in Peru, and I'm going there to do a POC in March. And with that, I'm going to have a pilot plant, and this will trigger, it's for the dewatering process, by the way. And this will trigger a very interesting perspective because I didn't get a pilot plant in Chile with BHP and Rio Tinto because my laboratory equipment is small. It doesn't have all the parts needed. Mainly, there is no trapdoor in my lab equipment. I removed the front of it to get access to the material after the test. And the water removal is done by a peristaltic pan, which in the actual pilot and commercial version will be done by Symphony. Put Symphony in such small equipment like I have, it's very impractical. So we know all the answers for it, and all we need is a little bit of a grant or investment, and we'll skyrocket. There is no shortage of market for these solutions.
I have a follow-up question, but I don't want to take up the floor too much. So,
oh, you're good.
So in one of the first slides, it mentioned using an acid. Is there any environmental concerns with that, or any concerns about residual particulates ending up in the acid again? I don't.
Right. Okay. Yeah. This is the kind of the chemical side of leaching, right? It can be acid. It can be an alkaline solution. Depends on what the recipe asks for. But thanks for the question, because I forgot to tell this. Once we have removed the leachable metal, there is a washing step I forgot to mention, that we're going to inject water to remove the left of the lixiviant that was left behind. And after the washing step, there will be a neutralization step, where, for instance, if we use acid as lixiviant, we're going to inject alkaline solution to neutralize the pH, right, of the material left inside the equipment. And with this neutralization step, the material becomes usable for closure and recovery of the area, mine it, which today, both in pile and tank leaching, it's not a common process done. They simply dump it with a altered pH in the tailing deposit or facility, whatever. So yeah, we are very much concerned about these environmental questions, and we know the answers to how to solve them, to make this material, which will be a clean, let's say, tailing waste, eco-friendly as possible. So we can dry stack, put on the ground, and then recover the area with a top soil layer, and everything will be okay.
All right. So Chris Sakimian, you have a question? You're muted, Chris.
Thank you so much. Department of Defense would have programs available to explore these types of approaches, but I would suspect you would need an American company to collaborate with in order to be considered for such a thing. Maybe somebody knows something that I don't, but have you investigated any potential collaborative arrangements with American companies in this business? Over.
Yeah, in fact, for the DOE program, we also needed an American company. So we incorporated a company in Texas. And so SmartDry is also an American company right now. And the problem with both DOE and DOD is the safety aspect, because when you're talking about mining uranium or cleaning up whatever, we're talking about low radiation, but still radiation. So you cannot do in your garage. And this has been quite a challenge to find one of the national laboratories to accept us as partner, to allow us to do the research and development in their facilities, you see. I'm talking to Idaho National Laboratory. I tried the laboratory in Scandia National Laboratory also. I'm participating, hopefully, let's see if I'm selected, in Cradle to Commerce in Barclays lab, National Lab. Also, those are the labs that are equipped and allowed to do research using radioactive material.
But beyond the radioactive, Fernando.
Beyond the beyond radioactive material, yes, we can. We're looking for mining companies in the U.S. that would partner with us to develop pilot plants, either for dewatering or mineral separation, leaching, inverted leaching, whatever the company.
Or dredging. Or dredging. I mean, but you could do that too as Stay Dry out of Texas. You could contract with the DOD if they wanted to do dredging, or if they wanted to clean up what used to be a live fire area or something like that.
Yeah, definitely. And we can create joint ventures also with, for instance, dredging companies and things like that. There is all possibilities on the table.
Right. Go ahead, Ryan.
Thank you.
Have you reached out to Pacific Northwest National Laboratory? Because
no, the only one that I'm talking right now is Idaho National Laboratory, because the other ones didn't answer my email.
I am with Pacific Northwest National Laboratory. I am not dealing with this sort of a thing, but we do have the Hanford site, and that usually makes things a lot more easy. So if you could put your email address in the chat, and I can ask around.
Right, do that.
Yeah, and Chris, I mean, you're tied in with AFRL. I don't know about NRL or ONR, but there might be some interest there as well. If you can share.
This Chris?
Yeah,
you Kimian?
Yeah.
I'm at OUSD R&E, but I'll tell you what, I will look into what the different, whether there's some defense manufacturing institutes that might go ahead.
Yeah, I was confusing you with Howard Meyer. I apologize.
Yeah, not me.
Yeah. All right.
This one last question. This slide deck will be emailed out, correct?
I don't email it out, but there is it'll be in the, I think it's already in the repository. So if you go to my website, on the top menu bar all the way to the right, it says file repo. That's the link to the file repository. You just log in with your LinkedIn account and you have access to the videos and the files for downloading there. On YouTube, you can't download the files, but they're easily searchable and findable. That's why I put them up there too.
Copy.
But if you need it, just let me know and I'll shoot you an email. Because again, Fernando also he was in the second forum that we held on polyplexus, and because we did not have the interactive, the live interactive portion like this, I felt like I was not providing what I had promised to provide. So that's why I'm bringing these different presentations back, so that to give them the full benefit of this live interactive part where we can exchange the ideas. So that presentation will go up as well on the YouTube channel. But please feel free, if it's easier, just to reach out to me. I can put it up on a Google link, or you can send me a DoD safe link or something like that. Anybody that is interested. All right. So what else, Fernando, what didn't we talk about this time that we might want to touch on?
Well, yeah, we are open to any kind of a collaboration, joint venture, and development that any branch of the government or private companies would like to think about. We have taken the development of technology from a tier 1 to 4, 5. We are ready to go to pilot and things like that. So we are, I think, pretty much in the right direction. But it's hard tech, and this it's not one very fast thing like software or things. But the market is there, the pains are there, and the opportunities are there. I mean, mining tailings is the new gold rush of the mining sector right now. Everybody is talking about. The problem is, what is the technology to recover these ultrafine grain? Flotation does not do well with it, and our technology does. We tested with zinc, iron, manganese tailings. We have the results. We even test with gold, meaning waste, right, from the Amazon, because illegal gold mining in the Amazon produce a lot of mercury contamination, and we think this can be a way to clean up the mercury also. We tested. We had some surprises that we are talking to experts in amalgamation, because it has to do with the amalgamation of using mercury and gold and what it is happening there. But other metals like copper, zinc, nickel, cobalt, we are very sure that using either mineral separation or inverted leaching, we can recover them. And there is a lot of metals in tailings around the world. Our calculation says there is something like $17 trillion worth of metals in the almost 300 billion tons of tailings spread around the world. Like there was an American company that tried to mine the copper tailings in Chile, and it was denied because it's going to use too much water. And in copper tailings in Chile, there is just 10% of iron. But because you don't have to grind, you don't have to mill anything, it's already done by the copper mining. It makes sense, especially at the price of the iron right now. And there are other things like decarbonization. These ultrafine grains are especially interesting for decarbonization process in steel industry and the other metals also. We are also looking into this here in Brazil, talking to Usiminas, CSN, which is our national siderurgical company that is privatized now. And there are very interesting things that our technology can bring to the table.
So there's a lot of environmental applications for this as well then.
Yeah, definitely.
And because you're talking about the mercury, and now one of the things I was curious about is the you're talking about that some of the processes that have been used in the past generate a lot of waste, and then that waste is just piled up. Is there recoverable material in that waste?
In every single tailing of it, almost, yes.
Okay.
For instance, in nickel tailings, right? Nickel mining tailings, there is a small percentage of cobalt. In fact, most source of cobalt are from the Congo, which is the only country in the world that has very high rich ore grades of cobalt. But apart from it, everybody mines from nickel. When you mine nickel, there is a small concentration of cobalt. But nickel is mined for, 150 to 200 years. Cobalt became something important after the electrification process when met. So there is a lot of nickel tailings with a small percentage, 0.5%, 0.7% cobalt in it. But we're not going to mine only the cobalt. We're going to mine the cobalt, the iron, whatever. Our technology allows us to change the mindset from I mine something to I mine all that is present in the material, which is a big step for the mining companies, but in the right direction with impacts in the environment also.
Yeah, thank you for that. Yeah, no, I can see the definite applications, and just think about places where they do that. I mean, they just California with all the gold mining, and there's got to be mercury issues all throughout the Northwest.
Exactly.
So
In California, the law of the contamination of mercury is 3 times higher than the federal law, because otherwise we won't have water, drinkable water in California. So bad is the mercury contamination there. And still there is gold in the tailings of the gold rush area. It can vary from half gram to up to 1.2 grams. The problem is that the mining companies are interested in mining the gold, but they don't have the technology to remove the mercury. So the local community say, no, you're not going to mine the gold and leave us with the mercury behind. If you want to mine the gold here, you have to clean up the mercury. Clean up the mercury using present technologies is too expensive. So we think we have a shot at it. Really think so.
So going into chemistry here, so water can be contaminated with mercury, correct?
Oh, yeah.
So would there be any benefit to using mercury contaminated water? And could you leach the mercury out of water that was contaminated by running it through your process or using that water in your process?
Well, yeah. We tested with the contaminated mercury, contaminated waste here, gold waste here in Brazil, and the most part of the mercury sinks down, sink to the bottom of the equipment as expected. There is a small percentage of it that went with the water out, right? And we are suspecting that this has to do with the amalgamation and linking with the clay part of the material. So, but yes, once we've done this, most of the material was clean from the mercury, which was our initial goal, right? So yeah, but you still need a bit of polishing to get to the right place. But we're going to do it.
All right, no, that's great. Yeah, no, I thank you for the new applications, the dredging application. I really appreciate that.
Thanks.
Did not think about that, and Chris, Ryan, your questions have been great in this whole session. I appreciate your attendance, and I appreciate your commitment to asking those questions and trying to understand and trying to identify these solutions along with the rest of the community. But you guys are leading the way, and I appreciate that. So does anybody have any quick questions before we go ahead and wrap this up for the day? Chris?
Well, I'll tell you what, I'm looking at the Office of the Undersecretary of Defense for Research and Engineering website, and I'm looking under the Advanced Materials Directorate, and they say advanced materials explore innovative new materials and novel manufacturing techniques that can dramatically improve many of the department's capabilities. Yada yada. But anyway, it looks like they might be interested in learning about some novel manufacturing techniques. So
can you shoot an email or something, and we can, Fernando and I can take a look at that.
Okay.
I appreciate it.
Yes, sir. Got
Hey,
it.
thanks for taking the time to do that. I appreciate that.
That's the way I roll.
Thanks.
And I am drafting an email, and we'll get it sent out internally on the PNNL side just to see if there's interest.
Great, I appreciate that.
It'll be out and sent in a couple minutes. So
what about Sandia? Would any of this fall in there, bailiwick?
I represent PNNL.
Got it. I can reach out to Sandia.
Short answer is I don't know. This is not my area of expertise. So
yeah, okay. I just looking at some of the stuff that they do a lot with energy there, and I'm guessing, Fernando, you'd be able to pull out rare earth metals and all that kind of stuff. So
yeah,
so there could definitely be benefits to getting other people involved. So
yeah, definitely.
All right. Then if that's it, I want to thank everybody for being here. It's another great session. We'll be following up with those of you that had interest and questions on both topics. We are the Innovation Ecosystem or Platform and Forums is on YouTube now. That's under Technology Ideation. The documents are all up on the document repository. So a lot of things going on here. I've been focused on a few things with getting the business going and getting relationships built. So I've been a little lax on planning for presentations for the schedule. If you guys are looking at the future, I'm gonna hit that hot and heavy. But next session we're booked and we got 3 presentations. Sorry that Square Robot wasn't able to make it today, but we'll get them back on. That was another one that was quite fascinating, where they can actually run their robots in a full fuel tank. And I'm looking forward to getting that information out as well. So thank you again. Thank you, Fernando.
Thanks, Adrian. Thanks a lot.
When I'm in, sounds like you're going to be busy when I'm in Brazil, so we may not be able to hook up.
Okay. Thanks.
All right.
Bye-bye.
Okay, talk to you later.
Cheers.
Bill, did you have something?